This is recorded lecture on Chapter 5, Part 2. We will begin with the cathode, which is on page 58. And this is slide number 18 in the PowerPoint. Last lecture, we talked about the tube housing. We talked about the evacuated glass envelope or metal envelope, which is the X-ray tube, and how that is fully evacuated, and it contains two electrodes, the anode, which is the positive electrode, and the cathode, which is the negative electrode. This lecture begins with speaking of the other electrode in the diode, which is our cathode. So the cathode is the negative side of the tube. So when we looked at the tube, remember that we looked at if I pull up that slide again, we said we have a positive electrode and we have a negative electrode. So we've already discussed everything on this side of the tube. So now we're going to look at everything on this side of the tube, which is basically our cathode and the filaments in that and what exactly that side of the tube does. So it's the negative electrode. It is actually what provides a source of electrons that we need in order to produce X-rays in that tube, meaning the electrons that we send across the tube to smash into the anode target actually come from the cathode. Specifically, they come from the heated filament on the cathode. So this picture right here, we're looking at the cathode from the front, meaning typically when we look at it in the tube, we're looking at it from the side. But if you were to look at it from the front, you can see that this particular cathode has two filaments. We call this a large filament, and we call this the small filament. And what these correlate to is large focal spot and small focal spot. And if you remember from our last discussion, the focal spot has to do with the resolution of the image, how sharp, how clear, how much clarity it has, because that's the actual spot on the anode where the electrons strike. And remember, we had talked about the line focus principle and the fact that when you angle the target, you can send the electrons across in a greater stream, but what happens is when they actually smash into the target, they're released in a much finer or narrower path when they come out the window, which gives us better detail, better spatial resolution, better clarity, all of those kind of things, which makes for a much better image. So we have small focal spot and large focal spot. The cathode is also around it. The other component is not only the filaments, but the focusing cup that surrounds it. And the purpose of the focusing cup is to actually focus the electrons towards the anode. So the cathode side is made up of filaments and the focusing cup. And it's actually connected electrically to do two different of the X-ray circuit. When we talk about how there's two filaments, that is typically what you will find in a general purpose tube is two filaments, both a large and a small filament. When they have two filaments, typically it is called a dual focus tube, meaning it has two focuses, a small and a large. Okay, and when we look on the control panel, how you know which one you're choosing is because typically on the control panel, you will see an option for a large focal spot and a small focal spot. So if you're typically doing extremities, you usually want to use small focal spot. And if you're doing larger things like the chest or the thorax, you typically will use large focal spot. And how that plays out is typically with a smaller focal spot, you tend to use more time factor. And when you use a larger focal spot, you use less time. So with larger areas like the trunk, like the chest and the abdomen, the reason we want to use large focal spot and less time is to reduce the chance of the patient actually moving. With extremities like hand, wrist, forearm, toes, foot, Things like that are much easier to hold still, and there's no breathing specifications required. Like, you don't have the patient hold their breath or anything. So much easier for a patient to hold still when you're doing an extremity versus trunk work. The filaments are a coil of wire, and that coil of wire is about the size of a filament in a toaster. When you look at the heating element in a toaster that actually toasts your bread, that's about the same makeup. They're typically made of tungsten, and they usually have 1 to 2% thorium added to them. So tungsten is number 74, and thorium is number 90. So they add those two metals together, which makes it an alloy. Okay, and the reason they use tungsten is because it has a very high melting point and it doesn't vaporize very easily. Thorium is actually a radioactive metal element that is added to it to increase the thermionic emission that will take place, meaning it'll increase the ability to release or boil off of electrons. And it actually, when you put these two metals together, because it's an alloy and it increases strength of the filament, you're actually helping to increase or extend the life of those filaments. Notice it says that the filaments are situated parallel to each other in the focusing cup, and they share a common ground wire, meaning they're next to each other in the focusing cup, but you can only choose either large or small filament. You can't choose both at the same time. Now, both of those filaments sit in a focusing cup, and that focusing cup is made of nickel, which is atomic number 28. And that focusing cup surrounds the filaments on the back side and on either side, meaning right and left, and the front is open and faces towards the anode target. Okay, and the reason that it's open is because you actually are going to send the electrons across the tube from the cathode to the anode once you are getting ready to make that exposure. The focusing cup has a negative charge, and basically what happens is that negative charge on the focusing cup helps to maintain or keep those electrons together until they're ready to be sent across. Now, typically we think of like charges repel, but the focusing cup actually works on electrostatic repulsion. Because the negative charge of the cup is greater than the negative charges of the electrons that are released, it actually forces it to stay together until you're ready to send them across. If that wasn't the case, then those electrons, when they were boiled off, would just start to go all over the tube and wouldn't really be as effective for us with X-ray production. Okay, so now we discuss the two portions of the tube, each electrode. So in this part, we're going to talk about what happens at the operating console or the control panel. So on the control panel, we basically select our exposure factors. Okay, and our exposure factors are our MA, our time, and our focal spot size. Okay, MA, time, and focal spot size. MA stands for milliamperage. Time is just as it sounds, like how long you're going to actually make that exposure. Focal spot size, we said, has to do with resolution. And the other thing that I didn't mention a minute ago is your KVP, or your kilovoltage peak, which has to do with how penetrating the X-ray beam is going to be. Okay, so we select KVP, MA, time, and our focal spot size. And notice it says when we first start to press the exposure switch, some of the electricity actually goes to the induction motor of the tube, which remember is on the anode side, and it starts to spin that rotor, and the stators start to spin that rotor and actually bring the anode up to speed. And remember that we said up to speed is typically 3,400 revolutions per minute on a general purpose tube. So it starts to spin the anode up to speed, and at the same time that that's happening, on the other side of the tube, on the negative side, the filament that you selected, whether it was large or small, starts to be energized until the specific degree of thermionic emission is achieved. Now, thermionic emission is the process of releasing electrons from a heated filament. And the part that actually determines how many electrons are going to be released from your heated filament is your MA and your time, your mass value, because mass affects quantity. So between choosing your MA and time, you're actually telling the tube how many electrons you want released from that heated filament. The KVP factor determines how fast those electrons will come from the cathode to the anode to smash into that target. All right, and remember, your focal spot size determines which film actually heats up. So when you start to press the rotor exposure switch, the anode starts to spin to speed, and the cathode starts to heat that filament that you chose to release electrons to make an electron cloud, which will come across and smash into the anode. When you prep the rotor, that's actually the first phase of a two-phase switch. That's why we call it a rotor exposure switch. So the first part takes care of the rotor spinning to speed and the electrons being released from the heated filament. The second phase of that switch is actually where X-rays are produced. Okay, and the whole process from starting to prep the rotor, heat the filament, and actually create the X-ray photons is literally done in milliseconds. Okay, so the whole process is very, very fast. When the exposure switch gets pressed, the voltage from the auto transformer, which is controlled by your KVP, passes through what's called a step-up transformer, passes through that step-up transformer, and actually is what controls how fast those electrons come from the cathode to the anode to smash into that to create the X-rays and how penetrating they will be. Okay, the voltage then passes through a rectifier to the anode and cathode. And remember, the anode is always positive and the cathode is always negative. Now, there's a lot more information on here. Don't feel like you have to understand all of this at this time. This is something that we actually build on, because a lot of these things that are coming up about the rectifier bank and the auto transformer and the step up and the step down transformer, that all has to do with the circuitry. And that is actually chapter 4, which we do not look at yet, but you will look at that in your second physics class. Okay, but what happens is the voltage is passing from the negative cathode to the positive anode. And what that creates, because they're opposite charges, it creates a huge potential difference between the two, meaning that when you're pressing that switch and the X-rays are ready to be released, the cathode is extremely negative and the anode is extremely positive. Hang on one second. Because that cathode is always negative and the anode is always positive, remember, opposites attract. So when that exposure is getting ready to be made, the anode becomes extremely positive, the cathode becomes extremely negative, which means the degree of attraction between them is stronger. Now, what determines how strong the attraction is? Your KVP setting. The higher your KVP, the stronger the degree of attraction. Why? because when you have 100 kVp photon, that is much more penetrating than a 50 kVp photon. So the faster that they come across and the harder they smash into that anode, that makes it have a shorter wavelength, increased frequency, and makes it more penetrating than if you were set at a lower kVp. Okay? So your kVp determines your potential difference because kVp determines the penetrating ability of those photons. Your mass value determines how many photons you actually need to create in that beam to pass through the specific part. Now, I already had said this, but in going back to kind of reiterate, the current on the cathode side heats the filament to a point of incandescence. An incandescent is white hot, so really, really, really hot. It has to heat to incandescence, and I will tell you that the minimum temperature for incandescence is 2200 degrees Celsius or 3,192 degrees Fahrenheit. So when it heats to incandescence, the electrons literally are released or boiled off from the filament by a process called thermionic emission. When that thermionic emission takes place, you end up building what is called a space charge or an electron cloud. Okay, either term is correct. You have an electron cloud or a space charge. Once the size is reached that you have determined by your mass value, the size of the electron cloud that is needed, what happens is at that point, it's called a space charge effect, meaning once it's reached that size, it's not able to release any more electrons because the size of the cloud is where you've determined it needs to be. It's not going to really go beyond that. So at that point is when you're ready to create the X-rays. Because at this point, you've got a large potential difference, which gives kinetic energy to your filament electrons, and that's from your kVp setting. You've got a way where that kinetic energy can travel, meaning you've got a quantity of electrons provided by your mass value. And then you have your target, which is the place where those will actually interact. Okay, so the electron cloud gets attracted to the anode because of the huge potential difference. And these filament electrons that are coming across will reach speeds of at least half the speed of light between the focusing cup and the target. And the electron cloud, remember, will flow from cathode to anode, meaning from negative to positive, and it will never flow the other way because it's a diode, meaning that electrons will only flow in one direction, negative to positive. Okay. Now, when they come across from the cathode to the anode, they smash into, ideally, the focal spot on this target that is constantly moving. Remember, we said that in theory, like right here would be the focal spot, the area where the electrons, so there are electrons here, they smash into that, and then it creates a photon of energy. Remember, all of these are photons because they're in waveform, right? So when they come across, they smash into that target, and they typically smash into the target at a depth of about 0.5 millimeters. Okay, when they smash into that target, they smash at about 0.5 millimeters. And what happens is those filament electrons interact with the tungsten atoms, and that's where you create 99% heat and approximately 1% X-ray. And the two types of interactions that are actually that take place at that particular time is all of chapter 6. It's basically characteristic interactions and Bremsstrahlung interactions, meaning there's two different interactions that take place at that target to create the radiation. Okay, so these photons right here are created from Brems interactions and characteristic interactions. And literally chapter 6 is everything that happens right here. Okay, so chapter 5 is just telling you about the X-ray tube and how it takes place. Chapter 6 is telling you what goes on right here. So you've got the X-ray tube. You can see right here they've drawn a little electron cloud. They come across, they smash, and then when they smash into that, it releases energy in the form of electromagnetic energy, which is our radiation. All right, and I will show you this on a visual video that accompanies this chapter. We'll go through all the parts of the tube, and I'll show you, attempt to show you exactly what I'm talking about when we're saying this. The last part of this, they tell you some things that we can do to extend our tube life, because remember, average tube life is about 5 to 7 years, totally dependent on its use. Meaning if you do the preventative maintenance and you take care of the tube and you treat it well and you don't overload it and you try and be mindful of what you're doing, it could very well last you much longer than 7 years. But at the same time, if it's the only machine that you're using and you're using it all day, every day, and you have a ton of patients coming through, it might not even last you 5 years. We had one tube at Waterman, Advent Waterman, that opened up. When they first opened, their tube in the ER didn't even last a year. It was so overworked and overused that it barely lasted 1 year, and that tube cost well over $250,000 for that X-ray tube. So you really want to make sure as a technologist you're preserving the tube as best you can to give it the longest tube life possible. All right, there's some things that actually shorten X-ray tube life, things like frequently using high or maximum exposure factors, using low but long exposure factors, like if you expose for a long period of time, and or if you overload the filament. So it has to all do with the thermal characteristics of X-ray production, and these are things that we absolutely can control, right? And we have to be mindful of that so that we don't clear out the tube before it's time. Now, there are built-in methods that help to dissipate or get rid of the heat, like the oil bath that the tube sits in inside the tube housing, and potentially it has cooling fans. The rotating anode also helps spread the heat over a larger surface area. And then using things that are very heat tolerant or have a high melting point also, when we make the tube, helps us deal with the heat load. All right, so there's 3 processes. Once that anode gets hot, there's 3 ways that the tube actually can get rid of or release that heat. It can do conduction by heat tolerant materials, like it can pass through the anode target and into the copper and the molybdenum, which helps dissipate the heat from the face of the anode. You can radiate heat from the anode to the oil bath that's in the protective housing, which will help dissipate some of the heat. And then if it has cooling fans, that also would help to blow some of that heat out of the housing into the room and help get rid of some of that heat that gets created. Because remember, 99% of what we create is actually heat, and less than 1% is actual X-ray exposure. Okay. Typically, modern units have a protective circuit built into them that does not allow the technologist to use an unsafe exposure technique. Like, it's very hard to overload the tube. A lot of times the tube will have an automatic shut off where it won't allow you to make the exposure if it's too high and it's going to damage the tube. Right? Even with that said, though, we have to understand that X-ray is still very inefficient. We're creating 99% of what we create is heat, and only 1% is radiation. So we have to be mindful of that when we choose our technical values and think about what we're asking the machine to do. All right, heat units. Heat units is basically a measurement of the amount of heat that's stored in a particular device. All right, and for the X-ray tube, there's actually a formula to calculate heat units. Now, these things right here, not sure why they're not showing up, but these should be multiplication symbols. So you multiply kVp times mass, or times MA, times time, times a coefficient. So each of these equals a multiplication symbol, either that or this. So those are multiplication symbols. So you multiply kVp times your MA times your time, and then the C represents a correction factor. Okay, and it depends on your generator type. So in the book, if you see it, it'll tell you that a single phase, you would multiply it by 1. A 3-phase 6-pulse generator, you would multiply it by 1.35. A 3-phase 12-pulse generator, you would multiply by 1.41. And a high-frequency generator would be multiplied by 1.45. So you can calculate how much heat is produced from one exposure. And if your exam required multiple exposures, then you could also note how much heat is generated for the entire exam. Now, why does that matter? Because if you just slow down a little bit in between your exposures, that can actually save some of the tube life. Okay? All right. Now, some other ways to extend tube life, you can follow specific warm-up steps that are set by the manufacturer of the equipment. You don't want to prep the rotor excessively, meaning since it's a 2-part switch, it is possible to push it down halfway and do what we prep the rotor. Sometimes when you have pediatric patients, you'll do that to help like get on the rotor so that you can watch the baby like breathe in, breathe out, breathe in, breathe out, so that you can time the exposure correctly. Sometimes we sit on the rotor, but that actually shortens the tube life, so we have to be very careful of doing that. Right? Ideally, you want to push the button all the way down so that you're not actually letting the rotor spin longer than necessary, because all that does is create extra heat in the X-ray tube, which is not good for the unit as far as lasting. And you don't always want to use extreme values when we do our exposures, meaning you don't want to use very high exposures all the time, because what it can do is actually pit the anode, PIT, makes a small area where it melts. And then when it does that, it won't output the radiation the way you want it to. But by the same principle, you don't always want to use very low, long exposures, because then that wears out, that can wear out the tube as well, in that it'll wear unevenly where the heat is created, and its excessive time factor can actually wear out the bearings in the rotor. So just making sure that we're using the equipment appropriately, following proper guidelines is just important to making that tube life last as long as it possibly can. We can extend that tube life. All right, and that concludes chapter 5 on the X-ray tube. I am going to put together a visual video for you guys to look at where I'll explain the different parts of the tube again. I'll have it, I'll literally draw it out for you, and I'll explain the process of X-ray production so that ideally it makes a little bit more sense. With that said, if you have any questions or comments or concerns, please make sure you write that down or note the question on the specific slide so that when we meet again live, we can discuss and hopefully I can clear up any confusion. Thank you so much.